Our next speaker will be Anthony Shaw, and he will be talking about unlocking the parallel universe, subinterpreters, and free threading in Python 3.13. Let's give him a warm round of applause.
All right, hey everybody. I'm super happy to get one of the last slots of PyCon and spend the entire time stressing about this. So yeah, really happy to be here. It's been an amazing conference, great to see so many people. And I want to talk to you about parallelism, subinterpreters, and free threading. And I'm going to demo something completely ridiculous at the end of this talk, where we're going to just run it all at the same time and do some testing. So if you're interested, my blog is at this address. I'm on Mastodon on the fostodon.org instance. I'm also on x.com, which I never get used to. Code samples, notes, links for everything in this talk are at that QR code. That QR code will also be on the last slide. So we're going to keep moving, but you will see it at the end. It's also got the links to all the libraries. And if there's anything I complain about in this talk, there's also a citation as to where somebody has made a point of why. There's some prerequisites for this talk. If you don't meet all the prerequisites, you need to leave immediately. So PyCon 2023, Eric Snow gave a talk on subinterpreters. Sam Gross gave a great talk on free threading in EuroPython 2022. There's also another talk happening right now, which you need to have watched. This is a talk on parallelism, so it would be amiss if I didn't make a parallelism joke. There's also building a JIT compiler for CPython, which happened an hour ago, and overcoming GIL with subinterpreters and immutability, which Yuri gave yesterday. Also, there's the chapter from my book on parallelism and concurrency, where I talk about subinterpreters back in 3.9. And you can read my master's thesis if you're really, really bored. Okay, so when we talk about parallelism, let's say it takes me an hour to solve a Rubik's Cube. How much time would it take 4 people to solve one Rubik's Cube? Right. Okay, so this is kind of the nature of parallelism, and when people ask for speed-ups, it's how able are you to segment a task? There's something else as well, which is if it takes me 10 seconds to draw a picture of a dog, how long would it take me to draw 4 pictures of a dog? 40 seconds. How long would it take 4 people in parallel to draw those pictures? 10 seconds, maybe? Okay, so let's test it out. I need 3 volunteers, hopefully relatively close to the front, that have a pen, okay? And we're going to test this. Okay, so put your hand up if you have a pen to hand and you can draw a dog. Okay, 1, 2, okay. So first of all, I need to pick all the task, because you can't just start immediately. I need to send you the task. Any second one? Okay, there. Third one. Okay. Close enough. I'm the first core, so I'm core 0. So whilst I'm sending you these tasks, I'm not drawing a picture of a dog. So I can now get on with it. Hold on. Okay. So that might take me 10 seconds, but that whole time, I've been sending tasks across. I had to make the task in a format that I could send, like a pickle. You have to unpack that piece of paper, draw it, and you have to package that and send it back. So whilst basically you don't just divide the time by the number of executors. I think this is really important, and I'm going to show you some graphs later on, and they're probably going to be a bit confusing because you're going to expect things to be fast, and they're actually slower. And the reason is because of the thing I just demonstrated. So in Python, we've actually got a few options for parallel execution. We've got threads, which are in parallel, will be in parallel. We've got coroutines, which run concurrently. We've got multiprocessing, which is fully parallel, and we've got subinterpreters, which are fully parallel. Each one has a different startup time, and this is the time it takes to start one of these. The smallest is coroutines. These run concurrently, and the largest is multiprocessing. I'll show you some benchmarks of that. And they have different use cases. So for example, if I took this task here, which is to calculate the difference between the number 50 for an array of random numbers. If I split that in half and executed it between two threads in Python 3.12, it would take twice as long. Partly because of the GIL, actually that's the main reason, but we can't run that fully in parallel on older versions of Python. So, in 3.11, the GIL lived in the interpreter, but there's a lot of caveats to that. So really, we had one GIL per Python process, and the reason you use multiprocessing is to get fully parallel code execution. In 3.12, we had the ability to run multiple interpreters using a new API, and each one had its own GIL. So it's the per GIL interpreter. This means, where previously we can run one thing at a time per process, now in Python 3.12 and 3.13, we can run two things at a time. And the CPUs, the operating system, will figure out which core is available and schedule so they can actually run fully in parallel. So, let's talk about speed for a minute, because this is where we're going to get back to our paper analogy. If we compare the differences to run a particular task between threads, subinterpreters, and multiprocessing, and when I say threads, this is without free threading. We'll get onto that. To calculate pi to 200 digits is 0.04 on threads. To 2,000 digits is 2.3 seconds. On subinterpreters, it's slightly slower for 200 digits. And for 2,000, it's significantly faster. The reason is because the time it takes to calculate pi is so small for 200 digits that all you're really seeing is the overhead of launching a thread and the overhead of launching a subinterpreter. So when it comes to multiprocessing, what you're looking at there is actually just mostly overhead. Okay, so the quick conclusion from subinterpreters, and we're going to go into a demo in a bit, is that subinterpreters are really like multiprocessing with less overhead and shared memory. I'm going to talk about shared memory, and if you want to watch Yuri's talk as well, he gives a really good explanation into the shared memory. Okay, so that's one model where we can run things in parallel, and I'll demonstrate how we can do this later in the talk. So free threading. So from Python 3.13 beta 1, which came out a week ago, you can disable the GIL. So at the beginning, I talked about splitting a task in half and running that between multiple threads and that actually being slower. From 3.13, if you have the GIL disabled, it will be faster because it will run fully in parallel. The operating system is able to schedule those two threads on different CPU cores, and they can run at the same time. In Python 3.13, there's a number of optimizations to make single-threaded code faster anyway. And remember that the GIL exists for thread safety. And that's a super important point. The free threading change introduces a new ABI, which is like API, but with a B. So you need special wheels and a special build of CPython. This, again, is really important, because when we look at compatibility later on, you need to consider this change. So ABI is the application binary interface. It just means if you're loading a module which has been compiled in a language like C, you expect the functions to look a certain way. So when you import the headers, if they don't look that way, then you're just sending bytes to who knows where. Okay, so the GIL in 3.12 is per interpreter, and we could run multiple threads on different interpreters that could run at the same time. In 3.13, with the GIL disabled, you could have a single interpreter, and you can run multiple threads which run at the same time. So the GIL has now disappeared, and I've put teeny tiny locks on the diagram because there are still some locks, but they're much, much smaller. Okay, so the steps it's taken to remove the GIL are really quite straightforward, and I'm not sure why it's taken so long to do so. Step one, is remove the GIL. Step 2 was to change the memory allocator and the garbage collector, which is still a work in progress. And there's a number of changes which are happening on both sides of this. And then step 3, which is the last sort of simple step, is to fix all the C code that assumed that the GIL existed and is essentially not thread safe. We're here. So it's feeling really optimistic. Everyone's super excited about it. And this bit is probably going to drag on for a while. So I think in terms of C extensions and compatibility, this is one of the major challenges with both approaches, subinterpreters and no-gil, and any other attempt that's been made to get sort of fully parallel Python, is what happens with the C code. What I've seen with the demos and the testing is if everything is pure Python, it works really nicely. Because the core Python team have got sort of full control over what the interpreter's doing. The complexity really comes with the C extensions. And the irony of that is, and if you're, again, really bored and you read my master's thesis on this, the irony of that is that the reason we have so many C extensions is because people have written them to optimize code because they couldn't run things in parallel. So that's where we are. It's going to take a while. So is it any faster? So I did a small benchmark this week, because again, this only came out last week, with the GIL on and the GIL off to calculate pi to 2,000 digits. And remember last time with threadings, it was slow. So with the GIL on, it's significantly faster with the GIL disabled. That's kind of what you would hope for, right? That if you run in a thread pool to calculate pi concurrently, it is using that across multiple cores. With subinterpreters, it is running concurrently. You've got a teeny difference, which is this 0.01, which is the overhead of spawning the subinterpreter. And then with the GIL off, it's slower. I'll go into that later, actually. With multiprocessing, it's kind of similar to what we saw before. And again, it's slightly slower. The reason is turning the GIL off currently makes Python code run slower generally. There's a number of specializations and optimizations which are disabled when you run with the GIL turned off, because the team is still sort of figuring out how to make that stuff really thread safe. So I would expect with the subinterpreters, those two bar graphs to actually be really close in future. Clicker stopped working. What's it doing? Okay. All right, so that's great. Hands up if your production workload includes calculating the number of digits in pi. No, right? It's completely impractical. These benchmarks are really cool. You can show people how much faster things are when you run something highly CPU intensive. Real code does not look like that. And whilst we can see this kind of significant speed up, when you actually apply it to real-world applications, you find that I/O has a major factor in web apps. It has a major factor in data science because you're reading and writing from disk a lot or over the network. So I think what is possibly a more realistic example is to look at the way that web applications are architected in Python. So at the moment, if you use something like GUnicorn, then the best model to run GUnicorn on a server is to have multi-worker, multi-thread. There's a couple of reasons for this, but what it does with multi-worker is you run multiple Python instances, processes, using multiprocessing, and GUnicorn handles this for you. So because each C Python process has its own GIL, the way that you run a web server that can sit on a machine with 8 cores is that you just run 8 versions of Python. And there is a sort of special process that sits across that and governs and coordinates them all, but that's basically how you get parallelism with web apps at the moment. The reason you run multi-threading, typically each worker you would run 2 or more threads. The reason you do that is because, yes, the GIL stops more than one thing from running at once. However, the GIL is actually released on a lot of I/O operations. So if you make a network call, if you're reading or writing from a socket, the GIL is actually released before that happens. So with web apps, a huge amount of the time it takes to process a web request is spent with I/O, whether that's making database calls, sending bytes back over the network socket. So it does actually make sense to have multiple threads, because they can be running at the same time, even though the GIL is there. So I wondered, would it make any sense, instead of having multi-process, to have multi-interpreter, multi-thread? And since I got nerd sniped by Euro yesterday, would it even make sense to have shared memory, which is one of the major features of subinterpreters, to have something like a cache for Flask or Django that sits in the process but can be accessed by all the subinterpreters? Okay, so let's have a little demo. Okay, so prerequisites for this. Oh, too many windows open, hold on. People have asked, you've written a book on C-Python internals, why are you not a core developer? The reason is all the core developers use like Vim and Emacs with all these crazy setups. And I have a dog in my code editor. And I actually turned off, I normally use Comic Sans as my coding font, and I changed that because I thought it would be unprofessional. So yeah, you need to compile CPython from source with two flags. One is disable GIL, and the other one is with experimental JIT, because why not? Beta 1 is actually too old. You need to run this from main. So you can't use the beta 1 tag. You need to run this from main. So once you've compiled CPython from source, you can then use that and reference that as a virtual environment. So that's what I'm going to do. So I've created a virtual environment, and I've set up this application. So to do my multi-interpreter environment, I'm using a WSGI and ASGI server called Hypercorn. I had a look at doing this with Gunicorn. Gunicorn's kind of, the way it's set up, didn't make it very modular to rip out multiprocessing and put something else in, unless I completely rewrote Gunicorn, which I really didn't want to do. So with Hypercorn, I think this approach is better. So what I've set up with this web server is that when you start it, it will create a pool of subinterpreters, and you specify how many workers you want, and then it will start each subinterpreter and tell it which application to load. Each subinterpreter then runs this script. An important thing to note with subinterpreters that differs hugely from threads is that each subinterpreter has its own site. So if you launch a subinterpreter, that subinterpreter imports modules. Whereas if you start a thread, that thread is running in the process. So you don't have to re-import anything. So each one will start the subinterpreter worker, and this basically just starts Hypercorn. So I'm launching multiple workers, and I'm going to start a little thread, which will listen for a stop signal, so that if I shut down the web process, it tells all the subinterpreters that they need to restart. I also need to bind them all to the same socket, so all subinterpreters are listening on the same socket. And then I've got a couple of other configuration things. But really, that's it. It was just 50 lines of Python and a few comments about what I was working on. So the worker itself will create a pool of subinterpreters and fill that pool, and then set up some logging and load the application. So let's run this. So I have 8 cores on my laptop. So it's launched 8 subinterpreters, and in each one it started the Hypercorn process. So we're basically running a single Python process with 8 GILs, and each one is running Hypercorn and running a Flask application. So I can see in my Flask app, I've got my hello world root, And the way I set up the logging was that each subinterpreter would have like a number. So in the log entry, you see like 4. That's the 4th one. So that's pretty cool. I was expecting an applause, but never mind. Thank you. All right. Yeah, so that's sending one request. So let's give it a few more than that. I don't know. Let's give it a concurrency. This is Apache Bench. It's a cool utility for spawning HTTP requests. Let's give it 1,000 requests just to warm the CPU up a bit. So you see in the log in the background, the different interpreters are all responding at the same time. And it's running in a VM on my Windows machine, so like I'm not expecting this to be ridiculously fast, but it's pretty good. So it's launched that process for us. Now something else we can do, if I can find my mouse, is that because we've launched subinterpreters in a single process, you can close a subinterpreter and start a new one. So for example, if I change my route and say, hello world, question mark, and save that, it will do a hot reload of the subinterpreters. So when I make another request to the web app, it'll have my changes live. So you can do live reloading as well, which again is pretty cool. So I thought, okay, that's nice. So what more could we do with this? So I thought, okay, why don't, in the subinterpreter, we start a thread pool with the GIL disabled, and then just see what happens. So this route, basically I've got a database and a set of users, 1,000 users, and I'm running a SQL query, and then I've set up a thread pool executor to calculate the star sign for each user. It's a very practical use case. Okay. This one's a bit slower. That's too slow. What's it doing? Yeah, that's not working, is it? Oh, okay. Just needed a kick. All right, there we go. So it's calculated the star sign for 1,000 users. So in a subinterpreter which has its own GIL, but then I also disabled the GIL, we can run things in parallel within a single subinterpreter. Why would you want to do this? Well, just because you've got 8 subinterpreters and 1 for each core doesn't mean each one has been pinned to a specific core. So actually it makes sense to think about how you can parallelize workloads within a worker. This was never possible before either. So whereas previously you had a process and you'd run 8 processes and each one had a single GIL, now you can run things in parallel and in parallel again, and you can lead the operating system to figure out how it's going to schedule the threads. So this basically gives us a different scale of parallelism that would utilize when the CPU itself is actually quiet. Because you don't always have every single CPU core extremely busy at any one time. And like I mentioned earlier, you've often got a lot of I/O operations which are happening. So whilst this demo might be a bit exaggerated, you wouldn't really use a thread pool to calculate star signs. It shows that you could actually implement parallel models within a thread and run those on a subinterpreter as well. Okay, let me go back to my slides. Thanks, PowerPoint. One day I'm going to learn how to use it properly. Thank you for your patience. Okay. So there's one last sort of question from this, which is, okay, you've shown subinterpreters and then running with the GIL disabled. would that actually just make more sense to run a single interpreter and then just run tons of threads inside that? And I think it kind of depends, because that makes sense when threading is the right execution model for the task that you're doing. But code doesn't use threading out of the box. And one of the next points I wanted to think was, if we're kind of comparing the approaches, and there was a question yesterday, you know, is it subinterpreters or free threading? Actually, I think that both models could coexist. And sometimes you want isolation in a separate interpreter because you're doing things like hot reloading on a web app. Or you don't necessarily, a lot of modules actually have locks inside them. So you kind of make sense to scale horizontally by having separate interpreters and then potentially using threads where you've got something specifically CPU intensive which can be run in parallel like that. Another point is async I/O. And asynchronous code does not use threads. Coroutines are not assigned or created to threads. So I think people have kind of misunderstood this one when they've disabled the GIL and they've run, I saw someone this week trying to do a benchmark of a fast API application with Uvicorn with the thread, with the GIL disabled. And they were like, oh, it wasn't any faster. And it's like, because it's not using threading, coroutines don't create threads. It was not going to automatically figure out how to run in parallel. So a good question here is, I think, how can async I/O work in subinterpreters, and each one has its own event loop. And then another point is with C extensions, is that they were all expecting there to be a lock. And once you've taken that away, we're going to see a lot of challenges where they were expecting a lock to be in place. Another point is, I think the winning solution is not always the best one. You know, this is actually going to be more about what's practical and how is the adoption going to work, how many changes are required from C extensions, and which ones are people willing to implement and change. So sort of in conclusion, I think that subinterpreters are a better solution for multiprocessing, or sort of parallel, for long-running workers like the one I just demonstrated. I think for a web app, this is a perfect solution. I think free threading would be a better solution for where people have created thread pools and they have a specific task they can easily segment and they need quick data exchange between them. And I think the Python ecosystem relied on the GIL for thread safety, and removing it is going to break things in unpredictable ways for some time to come. But we can't keep putting off the change. I think this needs to happen regardless. And there are some terms and conditions to all of these statements. So yeah, thank you for coming to my talk. The QR code, again, is up there if you're interested. And there's links to everything I've shown, including the demo. And we've got a couple of minutes left for questions. Cool. Thank you.
If anyone would like to ask a question, please approach the microphone and ask a question.
I'm finished with the picture of the dog. Would you like that?
Okay. That was more concurrency than parallelism, that one, I think.
Why is the datetime module not thread safe? Like, what's it doing there?
Scan the QR code, and then there's a link at the bottom of the gist with all of those bullet points, and there's links to the specific GitHub issues, because I thought I might be asked that question. There's actually 8 separate problems. Yeah.
All right, I've got some reading to do.
Okay.
Hi, thank you for your talk. I was wondering, you were mentioning that, for example, you said for Flask, subinterpreters are a good solution, but not for fast API. And here you mentioned they're not good for Django or for datetime module. So I wonder if there is any kind of list or rule of thumb, what is it good for? Or for example, some list of corner cases like these ones for which it's not supposed to be used?
Yeah, this list will change by next week. So Django doesn't work because datetime, because of issues with datetime. But I think that should be fixed by the time 3.13 is released. Fast API, I think actually is a good solution for subinterpreters because you've got multiple async I/O event loops in each subinterpreter. Fast API with the GIL disabled, I don't really see any benefit of doing that.
Okay, thank you.
Thanks.
Hi, I have a question regarding async I/O. A common pattern that I use is using await async to thread to basically chuck in blocking code into a thread. And sometimes that blocking code, can do CPU work. So I'm a little bit confused about what you said earlier about essential and threading not being, used together. But that's a common pattern that I see in a lot of work.
Okay, that's possibly an exception to that then. I think my point I was trying to make is that I think people assume that coroutines are somehow assigned can be assigned to a different core by the operating system, which is not the case. It's not like threading where you've got a low-level container like a thread, and the operating system can actually schedule that on a different core. With a coroutine, it doesn't work like that. It's more of a polling loop. If you put a thread in the coroutine, and you had polling between that, then that would probably solve that issue. But I would thought there would be better solutions. But yeah.
For the C extensions, most C extensions in Python fall into 3 broad categories, and the vast majority fall in the first one, which is just calling some synchronous C call. It doesn't have any Python objects in it, doesn't have any of the reference counting or anything else to deal with.
Yeah.
Have you already started thinking about the migration tools for helping people with some of the simpler C packages?
There is an issue, there's a discussion about that. It's definitely not done yet. The GIL only got disabled like last week.
I know, I'm getting way ahead of myself. I'm excited
with time,
for it.
definitely, a lot of people have asked, which is, okay, I maintain a C extension, what do I need to do to make it sort of thread safe? That needs to be written up. And the sprints are on tomorrow. So like, if anyone wants to help with that, I'm sure the C Python team would be more than willing to.
Thank you for the talk. I have a question about the evolution of subinterpreters and viability of using them. Do you think that the removal of the GIL is the primary reason we should start looking to adopt them, or was there a prior tipping over point when you think they become more viable?
I think the viability of using them is actually relates to both, which if you're just using pure Python code, I think both you could probably pick up and use straight away. It's the C extensions that make things complicated, because that's kind of where we get a lot of the, actually, I mean, you could write pure Python code, which is not thread safe as well, like that is possible. It wouldn't crash, but you just get weird behaviors. So yeah, the reason I kind of want to share this is because the technology itself has actually evolved to the point where I think it's kind of usable for these applications.
Thank you.
I don't know if I missed this, but a plug on your behalf. Those VS Code pets are on your GitHub page, which is cool. Question, for the removal of the GIL, is that seen as like the ultimate goal for all of Python, or you'll use it if you need it, but otherwise there'll be regular GIL Python?
The person standing behind you can probably answer that question.
Well, I can talk on behalf of the steering council, and they've only accepted the free threading GIL removal experimentally. I think the idea is that if it actually gets accepted, eventually that's all you get.
Okay.
So my question for Anthony, sorry, what?
Go on.
We'll explain that later. My question for Anthony is, isn't the optimal model to run one thread with async I/O in each subinterpreter and have one subinterpreter per core?
That would make a lot of sense, yeah. Yeah, and that's the thing I was demoing was running one event loop with a thread in each subinterpreter. And therefore, each event loop has got, on each core, has its own locks, it's got its own polling loops. And that's a super efficient way of doing it. that's the answer. Thank you.
What?
Nobody else?
Just a quick question for me. Thank you for the talk. Do you think that there's potentially an opportunity when we look at those C extension libraries to perhaps be written in pure Python at a certain point? Some of them?
Yes. I think the markup safe is one really good example, and if you look at, there's the discussion on markup safe about this. They've got pure Python and they've got a C extension part as well. And the C extension part, what they're trying to do is actually make that as small as possible, just to do the bit that's slow and put everything else into Python. And the goal of that is actually trying to simplify things, the maintenance, and also to make things flexible when there's these kind of fundamental changes happening in C Python. So markup safe would be a good example, I think, of where they're sort of like trying to strip stuff out of the C extension, where it just didn't make any sense to have it in C. Like that part of the code wasn't slow, it wasn't like hot code. But sometimes you need things to be in C, either because you've got a data structure that's much more efficient in C than it would be in Python, and you just get a huge speed up, or you're calling something that you couldn't necessarily call from Python.
Other than web development, what other applications are being developed using subinterpreters, as this opens up a lot of new functions for Python?
I think if you've got sort of data processing where you're trying to spread that across multiple workloads, I would love somebody to look at something like Dask, for example, and figure out whether you could do that, where you've got multiple workers which are listening for information and then processing it, sort of long-running processes. So for data science, that could be maybe the Jupyter kernel. I don't know if you could do that with Jupyter, but like something like Dask, I think that would also make sense. Yeah.
So is there a plan to be like able to transfer small self-contained objects across subinterpreters? I mean, I think of them as being a little bit like JavaScript workers, where I can like have a transfers to my post message and move the thing.
Yeah, the goal is to provide interfaces to share information between subinterpreters without pickling. Pickling is extremely slow, so you can do all the immutable types at the moment. You can share those. You can also share shared memory via memory view. So the one thing I wanted to build on next with this demo was to have a cache for the Flask app that's shared between all the subinterpreters, and they can read directly from that memory, and it's like an immutable cache view. And then if one interpreter wants to put an entry in the cache, they can send it as a message, and then the main one basically then seeds that in a dictionary. I think that's possible today, and that's kind of a different way of looking at it, I guess. If you need continuous data exchange of every different type, then probably threading pools is a better approach.
Thank you.
Okay, we ran out of questions, so thank you very much, Anthony, for your talk.